Hi all, this is Mr. Yeager for physics. We are going to look at today the topic or situation of inclined planes or ramps. Okay, so what we're looking at now is your object is on a ramp. Okay, it's not on flat ground anymore. So there's only a few things that really change about these problems, but we still call this a 2D force problem because we're going to have component forces. So let's go ahead and take a quick look at this. Let's say, for instance, all right, we have this object on the inclined plane. What forces would be acting on this object? Okay. Well, first off, we would have one of the first forces we have would be weight, and weight would have to still be acting straight down. Okay. And let me go and quickly add an angle to this inclined plane. They're going to give you some angle to the inclined plane. But one of the forces acting on this would be weight, and it would be acting straight down. Again, we got to make sure we don't make the mistake and draw it, down from the surface. It is straight down. Weight is always straight down from the object. Okay. The normal force would be pointing perpendicular to the surface, so up at an angle like this. All right. And so one of the first things we should notice is the normal force and the weight are no longer perfectly opposed to each other. So the normal force will not equal the weight. You can't just assume that they'll be equal to each other. They won't. All right? They won't at all. All right? The only other force that's probably going to be acting on this during certain problems, it doesn't have to, would be friction. And friction would be pointing up the inclined plane because obviously the whole point is the object wants to slide down the inclined plane. Okay? So, we have all these forces, but the thing is, no force is perfectly opposed to the other force. Okay? Normal and friction are perpendicular, so we can't add or subtract these at all. Weight is not perfectly opposite of either of these forces either, so I cannot add or subtract the weight from either one of the forces. So this means I need to do components for one of these forces. And then what we do is we go, okay, which force is not necessarily cooperating? All right? And we would say that the weight is the non-cooperative force. All right? The force that's acting differently from all the other ones. And so what I'm going to do is I'm going to do components for the weight. And so one of the first things to really understand with inclined planes is how to draw the components for the weight. What you do is you always start by drawing a component that is opposite of the normal force. This is going to be called the weight parallel. Okay? Oh, no, not parallel. It's going to be the weight perpendicular. Yeah. The weight perpendicular. All right? Because it's perpendicular with the surface. All right? What we do is we draw that opposite of the normal. That's always the first thing to try to do. Otherwise, you're going to get all confused with where to draw it. So this is perfectly opposite of the normal force. And then I draw a parallel weight component that goes down and touches the actual weight vector. If this is drawn nicely, which mine is okay, it's not perfect, we should be able to see that this parallel force is technically pointing straight down the inclined plane. All right? Sometimes we draw it up here. I don't anymore, but early on I used to tell people to draw it up here. You can always do that. But again, these are not real forces. These aren't actually existing forces. Weight is, but the idea is I can split that component up into two parts. Okay? I'm going to get rid of the one I drew right there. All right? And so this helps me answer a question here. What does the weight actually do? The components are telling me that. The weight perpendicular is holding the object on the inclined plane, while the weight parallel is what is forcing the object down the incline plane. So the weight actually has two jobs here. One, to hold it on the inclined plane so it doesn't just fly off some crazy direction. It doesn't go like this. That would never happen. Okay? The weight perpendicular holds it on the inclined plane. The weight parallel tries to bring it down the inclined plane. And so with that, if we recognize that, we can go, okay, now I can see, hey, the normal is going to work against the perpendicular, the parallel will work against the frictional force. The thing is, though, how do I figure out these two? What if I'm only given the weight? How do I figure out these two? Well, I need an angle. Well, here's a crazy thing. It turns out if you draw this correctly, just like this, the angle at the top of the triangle here, right at the top where you see me just draw it, the angle up there is equal to the angle of the inclined plane. These two are the same. All right? So if you do this correctly, these two angles are perfectly equal to each other. So if we know the inclined plane angle, I know the angle of the triangle. All right, at the top, they're always at the top. All right. So there's a couple rules I can give you for this. All right. A couple rules for inclined planes. All right. First one would be the weight is what separates into the weight perpendicular and the weight parallel components. The weight perpendicular and weight parallel. Okay. 2, the weight perpendicular will equal the normal force. The weight perpendicular will equal the normal force. If I go back to my drawing here, they are perfectly opposed to each other, and the object is not moving up or down from the inclined plane. Okay? Off the inclined plane, how about that? This then means the normal will be less than the actual weight, because it's only equal to a component of the weight. All right? And 3, the weight parallel will oppose the frictional force. Now, I don't say they're equal. Don't tell me that they're equal. They can be. I'm just telling you that these two forces will work together to create a net force going down the inclined plane. You'll often do net force equals weight parallel minus frictional force. All right? Now, if the object's going down at a constant speed, then I could say that they're equal to each other, if it's a constant speed. If not, clearly the weight parallel is going to be greater. Okay? So, how can we solve some of these problems? Okay? So let's start off with a pretty simple problem. Let's just say a 10-kilogram box is at rest on a 30-degree inclined plane. All right? And just like all the other problems we've done so far, basically I could tell you, say, I want you to solve all sorts of things. I want to know what the weight is. This time now I want to know what the parallel and the perpendicular weight are. I want to know what the normal is, the frictional force, the mu. I want to know what the net force is and what is A. Okay? So first things first, draw it out. Always, always, always draw the free body diagram. So I have weight going straight down, normal going up. Do I have friction? I absolutely do. Otherwise, this object's going to slide down. So there is frictional force. I can already make that assumption. The box wants to go down the inclined plane. It doesn't want to sit there, but friction is going to make it stay. Well, first off, the object's at rest, so I know net force is 0 and acceleration is 0. That's pretty easy. Okay, those two are 0 to each other. All right. I have a 10-kilogram box, so the weight will be 100 newtons. M times G, 100 newtons. Okay. So now, though, where do I go? And obviously one of the big mistakes I see people do is they'll go, normal equals 100. No, it doesn't. We need to draw out our components. So, let me draw my angle in here, 30 degrees. All right. I draw opposite of the normal force, and then down to the weight vector. This is my perpendicular weight. This is my parallel weight. This is 30 degrees at the top. Now, the nice thing about inclined planes is as long, again, as you draw it like this, it's always the same formula to solve for perpendicular and parallel weight. Where perpendicular is the adjacent side, so this will equal weight cosine theta. Weight parallel is always the opposite side, so this will be weight sine theta. And so if I plug this in, I can solve for the perpendicular and parallel weights. So this is going to be 100 times cosine of 30 degrees, and this will be 100 sine 30 degrees. This we know will come out to 50 newtons. I believe this comes out to 87. I'll double check that real fast. All right. Again, if you know your trig functions well, you probably already have that answer. Yep, 87. Okay. Okay. So good. So we know the weight parallel is 50 newtons. Weight perpendicular is 87 newtons. So now I only have the normal, frictional, and mu. Well, what did we say? Normal is opposed to the perpendicular weight, so they're equal to each other. So perpendicular, normal, is 87 newtons. Frictional force, I'm at rest, so it must equal my parallel force, 50 newtons. Coefficient of friction, 50 over 87. That equals 0.57. 0.57 is a coefficient of friction. All right, so that's the basics. Let's go ahead and go through one more, see if we can get it, see if I can come up with a decent problem. Let's say you have a 75 kilogram object slides down the inclined plane. -40-degree inclined plane. And the coefficient of friction and mu, just say n mu equals, we'll keep it simple, 0.1. Okay? Mu equals 0.1. I want to know what is the weight, what is the weight perpendicular, what is the weight parallel, what is the normal, what's the frictional force. I'm going to put mu there even though we know it. Mu, what's the net force, and what is the acceleration of this object. Okay? So, draw it out. Draw it out, draw it out, draw it out. Okay? I have my weight vector going straight down, 40-degree angle, normal perpendicular from the surface, and there is a mu, so that means there's frictional force being applied to it. All right, draw out my components. Down from the normal, down toward the weight vector. This is weight perpendicular, this is weight parallel. The weight would be 750 newtons, m times g, 75 times 10, 750. Mu we already know is 0.1. So where can we go from here? What do I need to solve for? Okay, I'm going to go for the perpendicular force. Perpendicular force is equal to 750 cosine of 40. Again, 40 is at the top of the triangle there. Weight parallel, 750 sine of 40. Solve for both of these. I'm getting 575 for this one. And 482 for this one. Okay. Looks good. I think we're going to be okay. All right. So I have my two components, 482 newtons, perpendicular, 575 newtons. What's my normal? Normal equals the perpendicular. So this is 575 newtons. Friction. Does it equal the parallel? It does not. You cannot say that for sure. It never says that it's moving at a constant speed. It obviously is not at rest because it's sliding. So I need to solve for frictional force by using the mu. Frictional force equals mu n, that's the old fun formula, 0.1 times 575, which equals 57.5 newtons. That would be my frictional force. Okay? So then how do I solve for my net? Well, this object is sliding down the inclined plane. So what are the forces in this particular direction of motion? That would be the parallel component bringing it down, but the frictional force trying to slow it back up. Okay? So weight parallel will equal, F net will equal weight parallel minus frictional force. So I do 482 minus 57.5, my net force acting on the object. is 424.5 newtons. So my last question is, what's the acceleration? Acceleration is net force over mass. So 424.5, since I squeeze this on in, over 75, will give me a velocity, or acceleration, not velocity, of 5.7 meters per second squared. So accelerating pretty quickly down this inclined plane. All right, that's basically it. You don't always have to have friction. Be prepared for problems where there is no frictional force, which means this is 0, and the net force will equal the parallel weight. Net force will equal parallel if there is no friction, because that's what's going to bring it down the inclined plane. Not many other variations to this. All right. The only other thing I might point out to you, this is a couple little tricks. Okay, is what if you want to find the frictional force quickly? Okay. Well, frictional force equals mu times n. Well, what did we say that n equals to on an inclined plane? N is equal to the perpendicular weight. So I could say this is equal to mu weight perpendicular, which is equal to mu weight cosine theta, which then is equal to mu mg cosine theta. Nothing that you have to specifically remember, but be prepared for little tricks here. Some people get all confused. Maybe I give you some information about this right away and you can plug it on in. Okay, if you have all those pieces, that would be your frictional force. All right. Don't be surprised to see that we write out weight perpendicular as mg cosine theta, like above, or weight parallel as mg sine theta. Instead of writing weight and weight, we write mg instead. All right. So just a couple little tricks in addition to what we just covered. You don't have to use these. Obviously, use them where you feel like they become necessary. I mean, just be aware of playing around with the variables a little bit. That's it. Thank you.